Okay, section 5.2 is a big section, integration by substitution. We need to just recall the chain rule that you take the derivative of the function and then derivative of what's inside. So for instance, if we have f of x equals x squared plus 5 to the fourth, then this would be 4, the derivative of this, and then we have to take the derivative of what's inside. So that's our chain rule, making sure that we take the derivative of the composite function. So formulas for our general indefinite integrals, we went over them in the last section. We want to make sure that we add our plus 1 and divide by that. So if we have derivative of function and with the chain rule, okay, so we have to make sure that we check the derivative of the inside function. So looking at our first one, our inside function is x to the fifth minus 2. The derivative of that is 5x to the fourth. So this is an integral of f of x, f prime of x, dx. So we can just add 1 and make sure we divide. So looking at this, our function and the derivative of our exponent is 3x squared. So this is just e to the x to the third plus c. Looking at the third one here, x to the fourth, the derivative of x to the fourth is 4x to the third. So this is the natural log function of 1 plus x to the fourth. So see if you can use the rules to determine the integrals for these three problems. But if we can't remember the rules, it's very easily able to do integration by a method called substitution. And first, in order to do that, we need to just explain or go over the definition of a differential. Okay, it's just an arbitrary real number. If we're taking the differential dy, then it's the derivative of the function. We just need to make sure we put this dx on the end. So looking at some examples, the differential of x squared is 2x dx. Differential of e to the 3x is 3e to the 3x dx. Don't forget you have to take the derivative of that exponent. And then taking the derivative of a natural log, finding that differential, it's the derivative of what's inside over what's inside. And then we need to make sure you put your dt on the end. So go ahead and try to find dy, du, and dv for each of these. And this is important for when we use substitution. So in order to do substitution, what you do is you find something that you can let a variable equal. So I'm going to say u equals x squared plus 2x plus 5. So that du equals 2x plus 2 dx. And if you parentheses, no parentheses, it doesn't matter. So then this would be the integral of u to the 7th du. And du represents everything else that's in there. And then I can take the derivative, or I can antiderivative this, anti-differentiate, and then substitute back in. So this is actually 1/8 x squared plus 2x plus 5 to the 8th plus c. And again, the more practice you do with these, the better you get. So go ahead and try the very basic one here. So looking at our indefinite integral formulas, just using a u, they're all the same as what we've been doing before. Okay, so the procedure, just want to make sure you select some kind of substitution that seems to simplify it, so that u and du is a factor, and then just evaluate that new integral and express the antiderivative in terms of the original variable. So let's look at some more examples here. So I'm going to let u equal x to the 3rd minus 5, du equals 3x squared dx, so that I have the integral of u to the 4th du. So this is 1/5 u to the 5th. And my u was x to the 3rd minus 5. And don't forget the plus c on the end. So I'm going to let u this time equal the exponent. So this is integral of e to the u du, which is just e to the u. So this equals e to the t squared plus c. And you have some examples here. Okay, let's look at the next example. Again, if I let u equal x squared plus 5, du equals 2x dx, I can see everything's there. So this is the integral of u to the 1/2 du. Add 1, and I need to divide by that. So this is 2/3 Okay, let's look at the next one. If I let u equal x to the 3rd minus 5, then du is 3x squared dx. But I don't have a 3 in here. So I need to make this 1/3 u to the 4th du. Then I add 1 and divide by that, which now this becomes 15. So this is 1/15 x to the third minus 5 to the fifth plus c. So you need to double check when you take your differential to make sure what's inside the integral there is the same. So let u be my exponent. Okay, but I don't have the 12 in there, so I need to make that 1/12. And the integral of e to the u is e to the u. So this is 1/12 e to the 4x third plus c. Next example. Let u equal the denominator. So now I have a negative 4. So this is going to be negative 1/4. And I'm going to make that a negative exponent. U to the negative fifth. I wouldn't have had to put parentheses there. So we add 1 and divide by that. So this is 1/16 5 minus 2x squared to the negative fourth. Or you could have it overwritten as a fraction. Okay, let's look at this one. This one's a little bit different. Because I don't have that x in there. So what happens is now you have to do a substitution for x. So x equals u minus 6. So now I can do a double substitution. I have u minus 6 times u to the 8th du. And we just distribute. And I should have had my du's in there. So let me just slide this over a little bit. So this is u to the 10th minus 6/9 u to the 9th, which reduces to 2/3. So I have 1/10 x plus 6 to the 10th minus 2/3 x plus 6 to the 9th plus c. So now you have some to try on your own. This problem and the last problem.